Okay, so today's topic is Newton's laws. This is one of the most important topics or chapters in a physics course because we use these ideas, these concepts over and over again. There are so many applications of Newton's laws in physics, mainly in mechanics side of physics. So I have written down the topics, the subtopics we're going to go over. So force, and then there are three laws of Newton. They're called Newton's laws of motion, so we're going to go over those, and some important terms such as mass and weight. We'll discuss about these things. These are terms that you are familiar with. We use these terms very commonly, but we're going to look into things like how to use these terms correctly in physics equations, what are the applications, what are the units, how to do math with these quantities. So we're going to go over some problems, like we're going to solve few problems at the end. So talking about Newton's laws, it'll be a good idea if you read the relevant book pages as well. There's some nice historical information behind this. Isaac Newton is a very famous scientist who set foundations of physics, lived few centuries ago. So I encourage you to go ahead and give it a try. Read some background information. There's interesting stuff like that. Okay, so let's move on to our first topic, which is force. Alright, so let's talk about force. What is force? I'm sure you're all familiar with the term force, that it's in very simple terms, it's a push or a pull, right? Force is like either let's say there's an object, let's say there's a box sitting on the floor and you want to move it. Let's say you want to move it to the left, so here you are, and you're going to apply a force. You're going to come closer to it and then extend your hands, and you're going to apply a pushing force. Now if you want to move it to the left, right, this is the direction, you have to apply a force in that direction. If you want to move it to the right, you either pull it or you come from the other side and apply the required force. So in very simple terms, a force can be explained as an action of pushing or pulling. But later you will see there's many different ways of talking about force. But for the time being, let's say this is the force, right? You're going to push this object across the floor. So the next thing is, what is the unit? How do you measure force? The standard unit, the SI unit for force, is newtons. Newtons. Measured in the unit, we give this name to honor Isaac Newton, the famous scientist I was talking about earlier, who set foundations to actually most of the mechanical related equations in physics. So measured in newtons, and use the letter symbol capital N to indicate newtons. So for an example, over here, in this case where you are trying to push this object, we can say you are applying a force equals 20 newtons, and it's important to give the direction. In this case 20 newtons, you can either put like an arrow like this to indicate the direction, or you can say 20 newtons to the left, right? So when it comes to force, you have the magnitude and you have the direction. So if a quantity has both this magnitude and direction, you know that we call it a vector. So force is an example for a vector. It is a vector quantity. Okay. Now throughout this discussion, I will be drawing a lot of diagrams to explain forces, and most of the time I will draw things like boxes like this, and we will be applying forces going to the right or the left, trying to lift it. So you can draw any object you want, like let's say you're trying to push a drawer across the floor, so something like this. But I prefer drawing boxes because it's easier, it's simple and easy to understand. So it doesn't mean that you can't draw any other picture, right? It's up to you, but for simplicity I'll be drawing a lot of boxes like this. So that is one thing I want to mention. And then to represent force, we always use these straight lines with a pointed arrowhead. So this is the standard way of representing a force, right? This gives you the direction, and next to this arrowhead you can write down the magnitude, whether it's 20 newtons going to the right, or it could be 10 newtons going to the left, it could be 15 newtons going up, or it could be something like this, 25 newtons making 30-degree angle with the horizontal. So whenever we are representing forces, we have to give the magnitude in newtons, and also we have to indicate the direction using an arrowhead or using a sentence clearly explaining the direction of the force. So there can be horizontal and vertical forces. Also there can be forces at any other angle. So these are things that you should keep in mind, right? Alright, so let's talk about simple mathematical operations with forces, like adding or subtracting forces. So you know that force is a vector, right? And it's a vector, it's measured in newtons, and it can be represented using an arrow. Alright, so let's say here we again going back to the same example. Here there's a excuse me, there's a box, and you want to apply a force of 20 newtons this way to the left, to the right, and let's say this 20 newtons, the force you are applying is not enough to move it because of the object is either too heavy or there's a lot of friction, something like that, some reason preventing you from moving it. So you ask for your friend. So your friend comes and he's going to give a push from the left side, so in the same direction your friend is applying 10 newtons. Okay, so here we have two forces, two vectors in the same direction. What is the resulting force? We talked about this earlier when we discussed vectors. If the two vectors are in the same direction, if they are in the same direction, 20 and 10, 20 newtons and 10 newtons, if they are in the same direction, you add them together, you get a larger force, 30 newtons to the same side, to the same direction, right? So the resulting force will be, I can either draw it here or I can draw it from here, it doesn't matter as long as they are in the same direction. So 30 newtons to the right. If the forces are in opposite direction, let's say two people are pulling on this object in opposite direction. You are pulling this way 20 newtons, somebody else is pulling this way 50 newtons. What is the resultant? Now the two forces are in exactly opposite directions. So 20 this way and 15 this way. Resultant is 5 newtons. You subtract now. If they are in the same direction, add them. If they are in the opposite direction, you subtract them. So this gives you 5 newtons to the right. We also talk about another example when the forces are perpendicular, when the vectors are perpendicular, something like this. So here we have 20 newtons, let's say this one is 10 newtons. Now there's 90 degrees between them, right? This 20 is in the horizontal direction, 10 is in the vertical direction. So in this case, a special case, right? The angle is 90 degrees. We can't do this if the two forces are like this, 20 and 10, but the angle is not 90. It's something other than, something less than 90. So in a special case like this, when vectors are perpendicular, resultant, we use the letter R for resultant. Resultant is equals to the first vector, let's say force 1, second vector, square of the first one plus square of the second one, square root. So in this case it will be 20 squared plus 10 squared square root. 20 squared is 400, 10 squared is 100, square root, so 500 square root. That's the resulting final total sum of the two vectors. So square root 500 newtons. So square root 500 is what? Square root 500 equals to 22.36. Now this force is going to go in between the two vectors, right? This is 10 going up, 20 to the left. The resulting force is going to go in between in a third direction, but it's going to go more closer to the bigger force, right? Out of this 10 and 20, 20 is the bigger force, so the resulting force is going to go somewhat closer. It won't take this exact middle path. It will be more like something like this, more closer. This angle will be smaller than this angle. Bigger the force, the resulting force going to get closer to that bigger force. Okay, so these are a few things we need to know before we proceed. Later we will talk about this situation. It's a little bit more complicated. So if the forces or the vectors are in the same direction, that means 0 degrees. You just add them, right? In this case, exactly opposite directions, that means 180 degrees between them, you subtract them. In this case, 90 degrees, you go with this rule. Alright, so this is how we add and subtract forces. Okay, so next, let's talk about Newton's laws. Let's start with Newton's first law of motion. Now, Sir Isaac Newton is a scientist who did a lot of research on motion of objects. Why things move, what kind of force do we need to apply, what's the result of applying a force on an object. Is it going to speed up, is it going to go in the same speed, is it going to change the direction of the motion, what is happening with the objects in outer space, like how do planets move around stars, so how do stars are moving in outer space. So he came up with three ideas, three laws, which really explains the motion we see around us, like how force is influencing motion. You do need force to initiate motion or make changes to motion, so let's talk about that a little bit in detail. So let's start with Newton's first law of motion. So think about an object. Again, let's go back to the same example where we have a box on the floor, or it could be your textbook sitting on the table. So right now, let's say nobody is applying any force. So can we say there is zero force? Actually, in a way, yes, we can. But on the other hand, there are some hidden forces which we learn later, kind of cancel out each other. For an example, in this case, this box always, it has its own weight, right? It has a mass. That mass is creating a weight. So this weight is pushing down on the floor, and the floor is pushing back. We call it the reaction force. This is the weight. This is the reaction, or the better word is normal force. Later, from now on, we will stick with the word normal force instead of reaction force. But the idea is it's kind of a reaction that's been applied from the floor against the weight. But on the other hand, these two forces cancel out each other. So they are equal in number, opposite in direction. So if weight is 100 newtons, reaction will be, or the normal force is also 100 newtons in the opposite direction, so they cancel out each other. So we can say that this box sitting on the floor, there is no net force. This word net force is important. There can be different forces, but if they're all going to cancel out each other, we say there is no net force. Now, the first law says if there is no net force acting on an object, the object will remain at rest. This is the first part. This is the first part of Newton's first law. All right. Excuse me. So let's talk about that one more time. It says if there is no net force, it's important to mention the word net. If there is no net force acting, T-I-N-G, acting on an object, right, object, it will remain, there's no space for me to write that, remain at rest. This is not entirely complete. We're going to add some more to this, but as of now, if there is no net force, if you don't apply any force, if there is no net force, it could be you are applying a force, but it's been cancelled out by something else, right? As long as there is no net force, the object will remain at rest. Even in this case, imagine you are applying a force like this, but there is a lot of friction between the table and the floor. The friction is pushing back. Friction is something always against you. So if this friction is large enough to overcome the force you are applying, imagine trying to push like a big refrigerator. It'll be difficult because there's a lot of friction between the refrigerator and the floor, right? This friction is large enough to cancel the force you're applying. You might need help of another person. I mean, it's not that you can't do it all the time. I'm just taking it as an example. Imagine like a huge, big fridge, right? A lot of friction. Okay, if there is no net force, things won't move. They will remain at rest. Part 2, the interesting part. Or either they will remain at rest or it will move in a straight line at a constant speed. Either the object will remain at rest or the object can move in a straight line at a constant speed. So that's kind of tricky. We used to think, or I used to think, that in order to move something you have to apply a force, and in order to maintain that movement you have to keep applying the force. I mean, think about pushing this box across the floor, right? You apply force, it moves, but the moment you take the force away, like you stop applying force, it will come to a rest, right? It won't continue to move. So what is this second part talking about? That even without any force, the object can move in a straight line at a constant speed. So these words are important: straight line, constant speed. In other words, the object can move at a constant velocity. When we say constant velocity, this is a vector. It makes sure that you are going in the same direction, right? Velocity means magnitude and direction both. So if the velocity is constant, that means your direction is same. That means you are going in the same straight line. You're not changing it, and how fast you are going is also constant. So as long as there is no net force, things can remain at rest, or they can move at a constant velocity. Means they can go in a straight line with the same speed. Now, the first part is okay. We all agree that as long as there is no force, things won't move. Now, the second part, it's hard to find 100% accurate examples around us. A close example is, think about a very smooth surface, like well polished surface, or like ice, very flat ice, a layer of ice. If you put this box, here's a very smooth ice surface. You have this box, you give it a push. Compared to a regular floor, this box is gonna go a longer distance, right? Because there is no much friction to slow it down, but there is always some friction, so eventually it will come to a stop. So that's what it's talking about. You give it an initial push. Once the object leaves your hand, right, after there is no contact with you, there is no force from you. The force is gone. The force is only during you had that contact with the object. Once the contact is off, there is no force, but the object is still moving. That initial motion wants to continue, but if there is friction, it's going to slow it down. If you find a place where there is no friction, this object can move forever, right? Without changing direction, without slowing down, it can continue. Even though we can't find real world examples for this second situation, we can find plenty of these examples if you think about outer space. If you go back to the slides, I have put a picture of a satellite. This is actually, as I remember, this is the Voyager satellite, which is now quite far from us. I think it was sent probably 25 years ago, I believe. It has gone passing the outer boundaries of the solar system. Now it's reaching that outer space regions, passing Pluto. So in outer space, there's hardly any friction. You throw something, it's going to continue in that straight line until it meets some other gravitational field, right? So things do move in straight lines without slowing down when there are no forces to change that motion. So that is the Newton's first law. We don't talk any numbers here, just the concept. So what you need to know is, as long as there is no force, either things will sit in the same place at rest, or they will move in straight lines without slowing down or speeding up. So that tells you, if you want to change the speed, change the velocity, if you want to speed it up or slow it down, or to change the direction, you do need some external force. You do need a net force. Okay, so that's the first law. Okay, so we talk about Newton's first law. Then we can move on to Newton's second law. But before that, we need to talk about one short topic, that is mass. What is mass? In simple terms, it's the amount of matter an object has, right? All these objects we see around us could be your textbook, the work table, yourself, the building, the vehicles on the road, anything, or the planets you see, like the moon. Anything that we consider as an object has some matter in it. The amount of matter is called mass. How do you measure that? The unit, the standard SI unit, right? SI unit for mass is kilograms. There are other SI units, grams, milligrams, micrograms, nanograms. So there are so many different other like this, but the standard unit is kilograms. And there are other old units like lbs and stuff, which we do use them in our day-to-day life, but when it comes to research or scientific studies, we're going to stay with standard units. All right, so the mass is measured in kilograms. It's the amount of matter. Mass is also known as a measure of inertia. What is inertia? Any object that has a mass has something called inertia. Again, inertia is also a fundamental property, that any object that has mass has inertia. Inertia is defined as the reluctance to changes, right? Imagine we have some big object. Let's say there's a big semi-truck, an 18-wheeler. So I'm not going to draw all the 18 wheels. Okay, we have this big truck here. It has a lot of mass, right? Maybe a couple of thousand kilograms. Now, let's say the engine is dead and you want to jump start this by pushing it. The battery is dead, so here you are. I don't know whether anybody has tried this. You're going to try to push this. Now it's going to be really difficult because there's a lot of mass, a lot of inertia. Compared to that, let's say you have a car with a dead battery and you're going to give it a jump start. Now you can't do this all the time, especially with vehicles with automatic gears. Now everybody has automatic gears in their cars, but if you are familiar with the stick shift, the manual one, when you have a dead battery, you can start the engine sometimes by giving it a push like this. Okay, so comparing these two, this semi truck is really difficult to move. It has a lot of mass. The mass gives inertia, so you do need to apply a lot more force. Bunch of people come together and they're gonna push this thing. Alright, now inertia is the reluctance, the resistance to change the state. Means that the truck was initially at rest, it wasn't moving, so to get it to move kind of difficult because of inertia. Now let's say somehow you manage to able to get this going. So now the truck is rolling down the road. Alright, it's coming down. Now you want to stop the truck because let's say there is a house. It will be really difficult to stop this also. Like you have to come from this side and give it a push in the opposite direction. That's going to be really difficult. Compared to that, the car is somewhat manageable, right? These are just hypothetical examples. Please don't try them. Just take my word. The first example is going to be very difficult. Truck is bigger, has a lot more mass, it has more inertia. Now the truck is moving. Inertia wants to keep moving. Inertia is the resistance to changes. It's moving, it does not want to change that motion, right? It want to maintain that. So that's the idea of inertia. So inertia comes with mass. So we say that mass is a measure of inertia. Inertia is again amount of matter, also resistance or reluctance to change of motion. If something is at rest, it's difficult to get it to move, and if the object is moving, it's again difficult to change that state. So this is the idea of mass, and the second keyword, inertia. We measure them using the unit kilograms. All right. Okay, so let's talk about Newton's second law. So in the first law, we talk about how objects behave, how things behave when there is no net force. If the net force is zero, either an object will stay at rest, means it won't move, or it will move in a straight line at a constant speed. Or in other words, if we combine the straight line and constant speed, we can say things will move at a constant velocity, right? That is when there is no net force. Like you have an object, for an example, here's the floor, here's a box, and there is no force. Either it will stay at rest or it will be moving at a constant speed. So that's first law. Now second law talks about what happens when there is a force. When there is a force, when you apply a net force, this is a net force. When there is a net force, what happens to objects? How do they move? So that's Second law talks about that, explain that in detail. So in one of the earlier topics we talk about mass. Now any object, that whatever the object we have that we are trying to apply a force, the object has a mass, right? So let's say here's the object, it's a box, and the mass is m. So this m could be a couple of kilograms, like 10 kilograms or something like that. Let me redraw this because that m doesn't look very good. So here's the floor, here's the object, here's the box you're gonna push across the hallway, and the mass of the object is m. And now you're gonna apply a force F. This F could be a couple of newtons, like 20 newtons or something. For simplicity, let's assume that there is no friction, right? This is a very smooth surface, like very well polished, very horizontal, no rough areas, a smooth surface, right? So we can say no friction. Why do I have to say no friction? Because when I apply a force, if there is a friction, let's go back to this diagram. I'm applying a force. Let's say I'm applying a lot of force, like enough force to move this, but there is friction, right? This is a rough surface. So the friction is kind of trying to work against me. It's pushing back, right? This is friction. It's always against you. You are pushing this. You are applying a force. So the net force is the difference of what you apply and what is friction is. So to avoid that complication, let's assume there is no friction. So if you apply 100 newtons, that 100 newtons is your net force. So this is the starting point of Newton's second law. After a lot of experimentation, what Newton realized was, when you have an object with mass m, and when you apply a force, let's say you apply a net force of F, the object, if it is free to move, right, if it is not attached to anything, if there's no friction, if the object is free to move, the object is going to accelerate. Net force creates acceleration, and we can say that this acceleration is proportional to the net force. So I'm going to write F net to indicate that's the net force. Acceleration is proportional to the net force. Now think about the situation. Okay, so let's come back to this real quick. What is proportional means? This little alpha looking sign, this says directly proportional. Directly proportional. What does that mean? Directly proportional means when you increase one, like let's say when you increase the force, if you increase the force going up, this arrow means it's increasing. When you increase the force, acceleration also increases. When one quantity increases, the other quantity increases. That's directly proportional relationship. If one decreases, the other one also decreases. They follow each other. So acceleration and force are directly proportional to each other. That means if you apply a small net force, the object is going to accelerate with a small acceleration. If you apply a large net force, you will have a bigger acceleration. So they're proportional to each other. Okay, so we have one relationship. There is another second important relationship. So let's say here's an object with mass m, and you apply some force F, and you get some acceleration. Let's say here's a bigger mass, has a big mass M. You apply the same force, F is going to be same, right? If this is 10 newtons here, you're going to apply the same 10 newtons. Now the mass is bigger. If this was, let's say, 50 kilograms, over here we have 100 kilograms, but you are applying the same force. What is the acceleration you can expect? Do you expect the same acceleration? No. It's a bigger object, you apply the same force, it will accelerate because there is no other force against you. It's going to move, it's going to accelerate, but at a smaller rate. So acceleration over here is going to be small. Over here, this is a big acceleration compared to this one, right? So the second relationship we have is acceleration proportional but inversely 1 over, no, I'm sorry, that's not how you write it. It's still alpha. It should be 1 over F. So let me erase this. Okay, do that, delete, cancel that. Alright. Oops, not yet. Okay, how do I do this? Alright. Okie-dokie. Okay, coming back to the topic. Acceleration is proportional to 1 over mass. So these are the two parts of second law. First one says, bigger the force, bigger the acceleration. That means force and acceleration are directly proportional to each other. Acceleration directly proportional to the force. Second part, acceleration and mass inversely proportional. That's when you write 1 over m, right? Proportional but 1 over m. That means when m goes up, a goes down, or vice versa. When m goes down, a goes up. Bigger the mass, smaller the acceleration. That's inversely proportional. That's an inverse relationship. So combining these two ideas, combining these two observations or experimental conclusions, what Newton did was he came up with a single equation. That single equation is acceleration proportional F over single relationship. This is not an equation yet, right? This is a relationship. And then after again a lot of calculations and experimentations, he found out that this proportionality relationship can be written as a simple equation, just an equation. So finally we have A equals F divided by M, right? So if we go back, we have two relationships. One relates the acceleration to force, the net force. The second one relates acceleration to mass in an inverse relationship. We combine them together, so we relate acceleration into a ratio of force and mass. And then finally, this is again, these are Newton's findings a couple of centuries ago, still works and it works really well. Acceleration is equals to F over m. So this is Newton's second law. Now this is how you write it. Now this is how you write it mathematically, but we're going to do a little modification. So I'm going to come back and write up here, right? We have acceleration equals F over m. But the most familiar form of this equation is we're gonna take this m to the other side and leave F on the left side, just cross product and switch the terms. Then we have F equals ma. So this is the famous Newton's second law. Force equals mass times acceleration. It comes from these two proportionality relationships, this one and this one over here. We combine them into a single relationship, then we change it to a single equation, and then we rearrange the terms and make it into this equation where F is on one side, mass and acceleration product is in the other side. So this is second relationship. If you think about the units, force is in newtons, this is in kilograms, acceleration is in meters per second squared. So these are the units. We have to measure mass in kilograms, we have to measure acceleration in mass per second squared, and the answer force comes in newtons. So we will talk about few examples of this. This is a very important, very useful equation. We will be using this again and again. This is second law. This tells you how objects behave when there is a net force. When there is a net force, objects going to accelerate. So that means there is no more staying at rest, there is no more going at the same speed. Things accelerate, they change the speed. Acceleration could be speeding up, acceleration could be changing the direction. Both things can happen when there is a net force. So it's always better to put a little net here so that we know we are talking about the net force. Not mandatory, not compulsory, you don't have to. F equals ma is just fine. So okay, this is Newton's second law. Okay, let's think about a simple example, a simple application of Newton's second law. F equals ma. Alright, so let's say there is a vehicle, there's a car that is 1500 kilograms, the mass is 1500 kilograms, and you're gonna start the car from rest. So initially it was at rest, and then it's going to reach the speed of 100 kilometers per hour within a distance of 55 meters. So let me write down the information. So it's a straight road, horizontal road. There are no inclines, there are no hills or valleys or anything. It's a straight horizontal road. So here's the car. Alright, and it says it's 1500 kilograms. Now it's going to start from rest, so initially velocity is 0, and then you start the engine, you start from 0, you're going to accelerate, right? You're going to hit the gas pedal, you're going to accelerate, and after 55 meters, after traveling 55 meters, so from the starting point, it's going to go 55 meters at a constant acceleration. It's going to accelerate. So it's going to accelerate constant. Now there are situations where acceleration also changing. Now acceleration means velocity is changing, right? The speed is increasing. So if we say acceleration is 2 meters per second squared, that means every second the speed get increased by 2. So if it was initially 0, a second later it's 2, another second later it's 4, another second later it's 6, like that. It's increasing at a constant rate. velocity is changing at a uniform constant rate. So that's constant acceleration. We can have changing accelerations as well. The speed is increasing at a changing rate, right? You are speeding up at some rate in the beginning, it's speeding up at a higher rate later. So that's a changing acceleration. Now in this class, we're not going to talk about changing accelerations. We're going to talk about the more simple version of it, constant acceleration. So whatever the acceleration, it's going to remain the same for that given piece of given section of the problem, right? So here we say that starting from rest, for 55 meters, the car is going to accelerate at a constant rate. So after traveling 55 meters, now the car is here. I need to draw the same looking car. Alright, now it's going at a speed of 100 kilometers per hour. So the speed has increased to 100, and during that time the car has traveled 55 meters with the, obviously you have to have an acceleration, right? Without an acceleration, how can even you start moving, right? Moving means you have to have some velocity. So initially you were at 0. So to get to some velocity, you still have to accelerate. Okay. So the question is, how much force need to be produced or supplied by the engine? To accelerate, you need a force that comes from the engine. Somebody has to provide it. Either somebody has to push the car, or the engine needs to generate that power and spin the wheels, right? Okay, so the question is asking how much net force, F net, how much net force need to be produced. So by looking at these information, now let's write down all the information we have in hand. We have mass of the car, 1500 kilograms. Do we have the acceleration? No, we don't. Question is, what's the force? What else we have in hand? We know that V initial is 0. V final is 100 kilometers per second. Now here's the thing. This final velocity is given in kilometers per hour. This is not standard units. We need to convert this. The first thing we need to do is we need to convert this into meters per second. Otherwise we can't use this number in our calculations. Also we have the distance traveled, 55 meters. Do we know the time? We don't. So we have some information in hand, and the question is asking what's the force, right? F net. Question is, what is F net? By looking at the problem, now this is how physics problems work. Sometimes the answer might not be very straightforward, right? Sometimes the answer needs like 2-3 prior steps. You can't get to the answer directly. You need to solve something else to come to the final answer. Now here the question is, how much force? We know that the mass of the car is given. So, and we know that there is an equation for acceleration. F equals ma combines the mass of the car and the acceleration to the force. So you can make an educated guess. Looks like this is the path we have to take. Think about the other equations we have learned, the kinematic equations. None of them have force in them, right? Question is asking what's the force? This is the only equation we have that has force in it. So it looks like we need to F net. We need to work with this equation. Okay, now to use this, we have the mass. Mass is already here, but we don't have acceleration. So once we figured out which equation we need, next thing is, okay, what are the variables we need to know. Now in this case we need to find acceleration. So this is our goal, finding the acceleration. So how do we get to that? Now look at the other information we have. We have all this: starting velocity, final velocity, the distance traveled. So if you go back, if you recall the kinematic equations, we talk about 3 equations. The first one is V final, V initial plus AT. Second one is V final squared, V initial squared plus 2AX. And the third one is X equals V initial time plus half AT squared. All of these equations have acceleration in them. Our goal is to find the acceleration, right? So by using one of these, we should be able to find the acceleration. Now the next question is, which equation are we going to use? So let's look at the things we have in hand. We have V initial, V final, and the distance. So equation 1 have V final and V initial. It has acceleration, which we need to, this is what we need to calculate, but it needs time, something we don't have in hand. So this equation right now is not useful, so we're gonna forget that. Now let's think about equation number 2. V final squared. We know what V final is. V initial, we start with 0. It has acceleration in it, and it asks for the distance. So this equation should work, because we have 3 terms. We have this, we have this, we have this. So we should be able to find the acceleration. Now if you want to check the third one, distance we have, V initial we have, again time we don't. So this also won't work. So this is the only option right now. So let's go ahead and start that. V final squared, V initial squared plus 2AX. Now all we have to do is plug the values. So we have 3 things. We have V final, we have V initial, we have distance. We should be able to find the acceleration. But there is one more thing we need to do first. V final, what we have is 100 kilometers per hour. We need to convert this into meters and seconds. How do we do that? 100 kilometers. So to make it meters, you multiply by 1000. And per hour, make this into seconds. The division part should be 3600. So cancels out, cancels out. 1000 divided by 36. 10, 20. Let's see. Let's find it out for, what's the number? 1000 divided by 27.78. 27.78 meters per second. Alright, so this is V final. This is what we need to plug into the equation. So we come here, 27.78 squared equals V initial, starts from rest, plus 2 times acceleration times 55 meters. Okay, so rest is just solving this simple equation and find the acceleration. So I get, I can write 27.78 squared divided by 2 times 55 equals acceleration. Therefore acceleration equals looks like my answer is 7.02 meters per second squared. So we found the acceleration. Now the question is, how much force do we need? How much force the engine should produce? So I'm gonna go, unfortunately because there's no much space, I'm gonna go up here and I'm gonna use F equals ma, Newton second law. Force is what I need. The net force produced by the engine is mass of the car, which is 1500 multiplied by 7.02 gives you I have 10,523.5 newtons. 10,523.5 newtons is what this engine need to produce. Okay. Alright, so this is how you work a problem like this. First, it's always a good idea to draw a sketch and mark the information in hand, and then write down all the known or unknown variables, numbers you think that's gonna be important, right? So you write down all that information in hand, and then see what we need. In this case, what we need is the force. So to get to force, which equation do we use? We're going to start with F equals ma. To complete that equation, what's missing? We see that acceleration is missing. So how do we get to acceleration? What information are we going to use to find the acceleration? So then you notice that we have enough information to write a kinematic equation and then find the acceleration. So we did that. We found the acceleration. We take it back to F equals ma, find the force. So this is a typical physics problem. Sometimes they're very straightforward. One step you get the answer. Sometimes you have to break it into sections, go section by section, solve a couple of equations. You have to be patient. You need to know the equations from previous chapters. You need this ability to combine all of them. So we will solve a lot of examples like this. I will discuss few more in these videos, and we will be discussing a lot more in class, right? So with that practice, I'm sure you guys will be able to solve these kind of questions. All right.